Okay, I'm Jonathan Hill with the Functional Chromophores Group, and I'm going to explain a little bit about the research that we're doing. So first I'm going to use these posters. We're making some organic molecules, such as these assemblies here. And one of the types of molecule that we're using is this kind of tetrapyrrole, which is called a porphyrin. And we're using these for sensing applications, for catalysis, and for energy applications. And we're also making some other molecules, such as these terphenyl derivatives, and these are used for sensing applications. A lot of what we do in the Functional Chromophores Group involves the synthesis of new molecules, and this is normally done by heating reactants and reagents using these apparatus here. So we use some hot plate, which can also stir and agitate the reaction, and oil bath, this is for heating. And there are some examples of the reactions here. And these are just to illustrate what happens in the reactions. The reagents and reactants are in the solvent, which is stirring. And by doing these methods, we can make new molecules. And after reaction, we generally end up with some black stuff like this, and we have to separate them. So we'll explain how we do this after. We end up after a reaction with a mixture of products like this, and we have to separate them out. So we can do this using column chromatography, and this can also be mechanized, or we use this instrument to do the separation. So we put our product here, dissolved in some solvent, and then force more solvent through it. And this is a special medium that can separate the products out. And there's also another problem we have. Some products are chiral, so they are like your hands. One is the mirror image of the other, and we use another special instrument to do the separation. So we've got a video. And here is Dr. Payne. He is busy setting up a separation. So this is the instrument we use to separate molecules that are identically chemically apart from being a mirror image. So we can use a special column, and it's similar to what I demonstrated before. The product is passed through the column, and based on what is contained inside, the separation occurs. And we can detect the signature of each compound as it exits the column using this. So these peaks here represent the products which are coming off the column. So is this a chiral one?
This is a chiral one, yeah. So the two peaks here are the two different enantiomers from the same product. So they separate relatively well.
Okay, so that's how we separate the compounds. But now there is a more modern way of heating reagents together in solvents, and that is using microwave reactor. And this is an example of microwave reactor here. And what happens is we add the solvents and reagents in a flask like this, and then insert into the microwave reactor here, and then heat using microwaves, which is much like microwave oven in your house. Okay, now I'd like to introduce Dr. Daniel Payne, who will show you some other techniques that we use in the laboratory.
So we have photo redox boxes, which is doing synthesis using light irradiation. So in this system, we have maybe 6 or 7 different light sources of very narrow wavelengths, so we can optimize. And reactions go in a reaction chamber, and then you irradiate with stirring for a period of time. So we have various new techniques for doing synthesis.
Okay, so one of our objectives is to prepare materials that can be used for antimicrobial and similar applications. And we do this in this lab here. And Diane is going to demonstrate what we do in this lab.
So one of our topics is preparation of new materials which are capable of producing singlet oxygen. Singlet oxygen is a reactive form of oxygen molecule which is famous for, or it's studied for its cytotoxic effect. The cytotoxic effect can be used for killing bacteria or tumor cells. We are now testing our materials on bacteria or the antimicrobial properties. For this purpose, we are using Streptococcus strain of bacteria.